What is the second part of the theorem is if U naught is any particular solution of the linear congruence AX congruent to B mod M, then there will be G solution and they are U naught plus M by G, U naught plus twice M by G and so on, where G here stands for the GCD of A and M. So how to find that? So here if you have U naught is a solution of the linear congruence AX congruent to B mod M, name it as equation 1. That is, because U naught is a solution, it means that A U naught will be congruent to B mod M. And assume G divides B. So let U1 be another solution. So if suppose U naught is any particular solution and if U1 is any other solution, then AU1 will be congruent to B mod and name it as equation 2. Take the difference of 1 and 2, we have AU0 minus AU1 is congruent to B minus B modulo M, or you can say that A into U0 minus U1 will be congruent to 0 mod M. Now divide both sides by G. And why we can divide it by G? Because G here divides A. Why G divides A? Since G being the GCD of A and M, GCD here means the greatest common divisor of A and M. So it implies that G divides A and G divides M. So we can divide throughout this by A upon G. Even in the modulo M also we can write. Why? Because G divides M. You refer to this from one of the properties of the GCD. How we get from here to here, why we can apply that? Because of one of the basic properties of GCD. So from here it implies that M by G divides, because A by G into U0 minus U1 is congruent to 0 mod M by G. By definition of divisibility, A congruent to B mod M, let me recall again, mod M, if and only if M divides A minus B. So here this is congruent to 0 mod M if and only if M by G divides A upon G into U0 minus U1. So M by G does not divide, since the GCD of A by G and M by G is equal to 1 from one of the basic properties of GCD that I have discussed in the previous first video. So therefore it means that M by G does not divide A by G. The only common divisor among this is equal to 1. So therefore M by G does not divide A upon G. The only possibility is that M by G must divide this term in the bracket, that is U0 minus U1. So if it divides here, again go back to this definition. M by U0 minus U1 is divisible by M upon G. It implies that U0 minus U1 will be congruent to 0 modulo M by G. Or you can write, adding both sides by U0 of this concurrence, it implies that U1 minus U0 plus U0, so U0 cancel, will be congruent to U0 modulo M by G. Or you can write here now U1 minus U0 will be equal to M by G into K, or we can say that U1 minus U0 is a multiple of M by G, that is there exists some integer K belong to set such that U1 minus U0 can be expressed as a multiple of M by G, that is M by G into K, name it as equation 3. Therefore for any K belong to set, for this K belong to the set of integers, when you divide it by G, okay, when you divide it by G, then by division algorithm theorem, for any K belong to set, divide K by G, then by division algorithm theorem, K here is equal to GR plus T, that is there exists a quotient R and remainder T, where T here is greater than equal 0 but less than equal to G minus 1, where G here stands for the divisor, R stands for the quotient and T stands for the remainder and K here stands for the dividend. So this implies that K can be expressed as GR plus T for some T which lies between this. Now multiply both sides of this equation by M upon G. M upon G is an integer, say, is an integer. Why it is an integer? Because G, since G divides M, it implies that M here is a multiple of G times into S, for some S belong to set. So therefore M by G will be an integer. So you can multiply both sides by M upon G of this equation. What we get is K M by G is equal to GR M by G plus T into M by G. Now K M by G in equation 3, replace it by this value. K M by G, that is this one from the right hand side of equation 3, replace it by GR M by G plus T into M by G. So when you replace it, what do we get is this. K u naught, u1 minus u naught will becomes Rm plus Tm by G, where T here is greater than or equal to 0 but less than or equal to G minus 1. It follows from equation 3. So from here, it implies that u1 minus u naught will be concurrent to, we can say that concurrent to Tm by G modulo M. Again, using this definition, A concurrent to B mod M, you can express it using this result, we can apply it here. So this implies that u1 at both sides by u naught, so you'll get u1 is concurrent to u naught plus Tm by G modulo M, where T here is greater than or equal to 0 but less than or equal to G minus 1. So thus any solution, what we have stated from the beginning is that if in the second part, if u naught is one particular solution of Ax concurrent, if Ax concurrent to B mod M, then another set of solution will be of the form u naught plus Tm by G, where modulo Tm by G, where T here stands for 0, greater than or equal to 0 but less than or equal to G minus 1. Thus we have the complete set of solution, or we can say that this any solution of Ax concurrent to B mod M must be concurrent, must be one of the following. Replace T by 0 here, what do you get? You will get u naught. Replace T by 1, you will get u naught plus M by G. Replace T by 2, you will get u naught plus twice M by G. Dash dash, you replace the last one is replace T by G minus 1, what do we get is u naught plus G minus 1 M by G. So thus we get a complete set of solution that, and moreover there are G solution here, as you can count from here 1, 2, 3 up to G minus 1 here, you will get G solution. So this will be the solution of a linear concurrence Ax concurrent to B mod M, concurrent to B mod M if you have u naught is one particular solution of this. Now the third part of the theorem is that any particular solution u naught can be obtained by solving this particular solution u naught. How to obtain it? It can be obtained by solving the linear concurrence A by B into X concurrent to B upon G modulo M by G, and this is possible since the GCD of A by G and M upon G is equal to 1. So let me just straight away discuss this with from the notes itself. Now to show that any particular solution, and moreover this part, it is pairwise, means all this they are pairwise inconcurrent. No two of them they are the same. For example, to verify this, for A u naught plus Tm by G is equal to A u naught plus Tm into A by G. You replace this, multiply here. So as A u naught is concurrent to B, so this can be written as, this whole thing can be concurrent to B mod M, as A upon G belong to Z and A u naught is concurrent to B mod M. And now we show that no two of them is concurrent to one another. And for that, if you suppose they are concurrent to one another, that is u naught plus I into M by G is concurrent to u naught plus J into M by G modulo M, where I here takes the value 0, 1, 2, 3, G minus 1, and G also takes this value with a condition here that I and J they are strictly less, I mean I is less than J. Then as you can see, u naught and u naught can be cancelled. It implies that I into M by G is concurrent to G into M by G modulo M, so that M divide the difference of these two, that is I M by G minus J M by G. M by G you can take common, so M divide this. So this implies that M by G into I minus J is a multiple of M for some K belong to Z, which implies that I minus G here, I minus J divided by G, M and M can be cancelled, so this implies that I minus J divided by G is equal to K. So this implies that G divides I minus J, but this is not possible. Why? Because I is strictly less than J, so therefore the difference of these two is much less than G, which is not possible. And why it is not possible? Because why we get a contradiction? Because we have assumed that suppose there are some of them they are the same, means they are concurrent. They are pairwise concurrent, means two of them, they are the same. So therefore, hence, all the solution u0 plus m by g, they are all different or they are distinct, we can say. In other words, they are pairwise incongruence, means no two of them, they are the same. Last part of the theorem, how to obtain that particular solution, is that to show that any other solution x0 plus m by g into s is concurrent modulo m to one of this x0 plus m by g into t. So by division algorithm, we have Q and R such that when you divide S by G, what do we get? When you divide S by G, you get a quotient cube here and a remainder R such that S can be expressed as G cube plus R, where R here is greater than equal 0 but less than equal to G minus 1. So hence x0 plus m by G into S is equal to, you replace this S here by this cube G plus R, so you have x0 plus m by G into G cube plus R, which can be written as x0 plus G and G cancel, so you have m cube plus m by G into R. Multiply this m upon G inside this term, inside this bracket, so we have x0 plus m cubed plus m by G into R, which is same as x0 plus m by G into R plus m cubed, which can be written as this one. So this implies that x0 plus m by G into S is concurrent to x0 plus m by G into cube modulo m by G into R, sorry, m by G into R modulo m. And how we can talk it, because if you have x is equal to ak plus m, this is same as x is concurrent to a mod, or we can say that, okay, sorry, if x is concurrent to, or we can say that if x is equal to a plus km, then this always implies that if and only if x is concurrent to a mod m. So use this. So here also x0 plus m by G into R plus m cubed, this is same as x concurrent to x0 plus m by G into R modulo m. So therefore, to obtain the solution u0, any particular solution u0, then we can obtain it from that m by G, from that linear concurrence a into m by G concurrent to b by G modulo m by G. And why we can talk about that? Because the GCD of a by G and b by G, m by G is always equal to 1. So this complete the proof of the theorem, which is an important theorem. So based on this, we will discuss some of the problems, how to find the example, how to find this, and whether the given linear concurrence has a solution or not. It depends on the GCD of A and M. If the GCD of A and M divides B, then we can say that the linear concurrence has a solution. And how many solution? If the GCD of A and B is equal, say 5, then the number of solution of the linear concurrence will be equal to 5. And what are those solutions? We can find using this theorem. Okay, so that's all for the theorem. In both video 1 and video 2, I have completed the proof or the discussion of this part 1, 2 and 3 of the main theorem. So in the next class, we can discuss the problems to find the solution of linear concurrence AX concurrent to B mod M based on this. So that's all.